Hello, everybody. Good morning, good afternoon, good evening, wherever you are in the world. Just want to welcome you to our webinar. We have our speaker here, Dr. Boniak, for the webinar, A Journey into Petroleomics. And we're just going to give it one more minute to let everybody jump in on the call. The webinar will last for about 45 minutes, and we'll have a brief section for questions and answers. So feel free to put any questions you have in the chat. And I want to thank everybody for taking the time.
Let's give it another minute and then we'll get started.
All right, everyone is still kind of coming into the webinar here, but just for the respect of everyone's time, we're going to go ahead and start. So Kushal, if you'd like to introduce our speaker.
Yes, absolutely. As Megan said, good morning, afternoon, evening, everyone. Thank you very much for your time and joining the webinar. I would also like to thank our speaker, Dr. Boniak, for his partnership with Bruker and doing this webinar on petroleomics and asphaltene. Dr. Boniak is an associate professor at the Federal University of Goiás in Brazil, specializing in mass spec for molecular identification and complex mixtures. He holds a bachelor's degree and a PhD in chemistry. As a head of chromatography and mass spec laboratory, his research focuses on innovative analytical method for crude oil and related products. He's made significant contributions to petroleum research and serves as a counsel on the general secretary for ALAGO and an affiliate member of Brazilian Academy of Science. Dr. Boniak is an associate editor of the journal De Química Nova and a board member for JSMS. His work has earned him a spot of the Analytical Scientist Top 40 Under 40 in 2022. So welcome, Dr. Boniak, and I will turn it over to you.
Okay, thank you, Kushal. Thank you, Bruker, for this pretty nice opportunity to show here today a little bit what we are doing in petroleomics here in Brazil, specifically at Federal University of Goiás. First, good morning, good afternoon, good evening for everybody. Here in Goiás, it's afternoon. It's lunchtime. Hopefully that everybody is seeing my screen. I don't know. Okay. Yeah. Today I will talk a little about petroleomics, passing through asphaltenes and through crude oil. The aim purpose of my talk here today is not only to show how characterize asphaltenes in crude oil, but ultimately what we do, what we handle this length of data that we get routinely from the samples in a applied way to petroleum industry. First, just a few minutes to show where I'm from. I don't know if everybody is familiar with Federal University of Goiás, but we are located specifically in the center of Brazil, near to our capital, Brasilia. These pictures here, it's our campus. It's quite far from downtown, but it's a pretty nice campus. And here it's a picture of Goiânia city, where we are located. Jumping in our subject of the day, I have here a slide showing what's petroleomics, just for introduction. Petroleomics aims to a comprehensive molecular characterization of petroleum using high-resolution mass spectrometry but and so use this composition to make some relationships between petroleum properties and their behavior, and so on, and ultimately have some enable us to create some models to predict these properties and this behavior. So here I have a schematic of this. We have the FT-ICR, the SolariX system. We have the MES spectra. So you assign molecular formula for each one of those peaks. You have this formula profile here, this class profile, and you have two properties, non-biodegradated and biodegradated crude oils. You see this class behaviors is totally different, and you can use models, geometric models to perform this kind of information in a feasible way. So,
Dr. Boniak, I'm sorry, I don't mean to interrupt, but can you put yourself in a presenter mode? We're seeing your slides.
Oh, sorry.
Sorry, we just received that comment, so.
Okay, this is
better. Perfect.
Okay, sorry, because I have two. Sorry, two. Yeah.
Perfect. Thank you.
And this comprehensive characterization can be used at the crude oil industry in different steps. Since the okay, let me see here. In different steps, and we call this key, a master key that can be used in exploration area, for example, to monitor deposition, environment, thermal maturity, biodegradation. All this information is so helpful to create models to minimize risk associated with this area. So petroleomics can be very applied to productions, for example, to study the emulsion formation, which species in the crude oil are responsible to perform stabilized emulsions, and which species on crude oil composition are related to the drawbacks normally found on flow assurance, for example, the asphaltene and naphthenic acids and so on. And in refining process, petroleomics can be very useful to predict properties, to see monitoring acidity, to forecast some problems that can be happen before they are on the field. And for example, at the logistics, ultimately the last step, the product quality and the stability, for example, the low sulfur diesel, the new biofuels, the new green fuels that can be very characterized very well using these tools. So to perform this science, petroleomics, we stand on mass spectrometry form using different corn storms. And to do that, I need ionization, these three prerequisites: ionization, ultra high resolution power, and data process. Regarding the ionization source, in mass spec, we have different ionization techniques that can be used to access the crude oil composition. But unfortunately, we don't have a universal ionization source that can be handled since non-polar compounds to polar compounds in a unique way. In despite of that, what you use is take a different snapshots of the crude oil composition to reconstruct, to create the whole picture of the oil. And the most used ionization source, if we go to the literature, we see electrospray Electric spray is used to mostly to access the polar compounds, and APPI. APPI, it's an opposite way of electric spray because APPI are related mainly to the aromatic compounds, but they can be, for example, access thiophenes, for example, and APCI can be situated at the middle between polar and non-polar, but depend of the strategies used in APCI. For example, modify the solvent. You can access, for example, hydrocarbons, but this is a new topic that needed more investigation on that. And ultra high resolution. Why you need ultra high resolution to perform petroleomics? Why it's mandatory ultra high resolving power? Because we are leading with maybe one of the most known complex mystery. And for example, if I select the peak MZ 4580, I have a plenty of possibilities just using with different molecular formulas. So when I have, so to separate these molecules with different elemental composition, we need to have an instrument that can be useful to separate this tiny difference of mass. So in a low resolution, I see everybody together, and using the FT-ICR, for example, you have the possibility to separate, to resolve this completely different species, and so on attribute molecular formula for each one of those peaks. This is the elegance of the high resolution and making the life more easier for example, specifically in this area. Just one example, this is a typical profile of crude oil, normally obtained in FT-ICR MS. And just to zoom in this region of 0.2 millidaltons of span, you can see 16 peaks. And for each one, it's possible to assign a molecular formula with accurately and test and check with isotope of each peak if it's correct or not. So resolving power is mandatory. And based on this resolving power, we have just 0.2 Dalton, 16 people, imagining a whole mass spectra. We are facing with a lot of peaks, and you need two strategies to handle this data. And Petroleomics has a specific language to treat this data. And mainly this language is based on 3 levels. All molecular formula assigned from the mass spectrum, we are classified and are categorized by class. And this class is the kind and the number of heteroatoms that molecular formula has. For example, all molecular formulas with 1 nitrogen, it's classified as class N, where molecular formula with 1 oxygen, it's class O. If you have here 2 oxygen, class O2, and so on. And so you can organize this and flash and in specific sheets for class, and go on and dive on this data. What Petroleomics, normally what you do is sub-classify in a second level of information. It's regarding to the DBE, the number, the total, the double bond equivalent. For example, the pyrrole here present in here we have 1, 2, and the rings 3 in saturation, 3 equivalent of dB, and this enable us to organize in a strictly way all these peaks identified on mass spec. The third level of information is related to the carbon number or the alkyl chain. For example, if I have the class N and see the dB3, what I see, because crude oil has a continuous, I see different species with different carbon numbers. So I can organize this in a pretty nice way and see in a feasible organizing this all information together. We can use that for perform some interpretation regarding to the question that was addressed before the analysis. So to see that all this information, we normally use some graphs. The most used graph is the class distribution. We organize the number and the abundance of each compound detected and assigned in a class profiles. You see this typical, and I select, for example, the 2O2 compounds. I can see a whole dB distribution in one specific dB. I have the all carbon number distribution. So this is this 3 level of information that I can normally use here to try to answer the questions what are addressed for us before the petroleomic analysis. And for example, you can reorganize all this information in ternary plots, just plotting here the relative abundance of the N and O and O class, and I can see easily separating these 2 type of oil from a lacustrine environment and a marine environment. So it's the whole picture of what we normally petroleomic face with the data. So, and today to show how to apply, this is a more fundamental point of overview of petroleomics. But what I have here today, it's a couple of examples showing how apply that for asphaltenes and crude oil samples in an applied way. So asphaltenes, it's a well-defined, it's a fraction defined by solubility. It's insoluble on an alkanes, but soluble in toluene. Asphaltenes are related to a big issues on flow assurance, because this can easily flocculate and form aggregates. And what happened is clog these pipelines, for example, and it will be a very harmful for the entire productions. So asphaltene has been studied for a long time, and the asphaltene history is replete of controversies. Mainly, the most important controversy is related to the asphaltene molecular weight. For a long time in literature, it believed that the molecular weight were even some papers show more than 10,000. But recently, mainly on the work done using FT-ICR the last decade, we see that what we are measuring before using a specifically top instruments, it's the aggregates, not really the molecular, the monomers, the molecular that are it's asphaltene is composed. So nowadays it's clearly that asphaltenes are composed mainly by molecular ranging to on average 500 Daltons, and but nowadays the main question is regarding to the type of structure of the molecules that are present in asphaltene, because you have from the production from the refine, when you put some asphaltene, for example, the content of asphaltene, you see pyrolysis products, mainly derived from the the alkylation of the alkyl chains. But sometimes we see these small pores related to the broken these alkyl bridges here. And so there are two type of model from these molecules, these asphaltene molecules. It's related to island and archipelago type compounds. And recently, the work from the MEG lab, specifically Chacon Patino, show in an elegant way selecting these asphaltene ions in ICR. Doing fragmentation, you can see this behavior from some island and archipelago structure, and they both are present on the asphaltene. And sometimes, depend of the way to extract the asphaltene, you see more island, other side we see more archipelago island type of compounds. So to handle it with asphaltene, because it's big issues on mainly on the flow assurance, you need to investigate deeply the composition and try. And in industry, they want to know to forecast these problems and handle this problem in the elegant way. And to do that, you need to dive in deeply on the composition characterization, and so you ultimately use this composition to create models that can be very useful to forecast or predict how this precipitation or how these things will be happening on field. So the goals here, it's what we did in this field here in my lab. It was superfractionate asphaltenes, and characterize them using LEDI. The goal of this work is measurement the stability of this asphaltene subfraction by turboscan, because you can monitor with fraction one more unstable than others, and link this composition with this asphaltene stability from our data. And so on. One question is different type of oil produce different kind of asphaltene molecules. You apply that using a geochemical assessment point of view. The method we adapted. We put an epithene, precipitate, take for example 24 hours, filtrate the asphaltenes, and so we try to exhaustively extract the maltenes from asphaltene, washing these asphaltene samples for 120 hours to allow us just to see the asphaltene and anything different, mainly maltenes, because maltenes has more feasible response on whatever ionization source that you use in mass spec. So, then we use the method proposed by Chacon Patino to fractionate these asphaltene samples. We did different a range of solvents, and using different time to collect different 8 fractions, and these fractions was surrogated, scrutinized by LEDI. Our main goal, firstly, original idea was use APPI to do that. It's mostly related on literature, use APPI, but unfortunately, this sample that we are investigating here was so unstable that clogged our capillary systems. So we developed a way to avoid, because when I use LEDI, sometimes you can form artifacts during the analysis. The laser the condition of LEDI was optimized to avoid the fullerene formation, and you can have this type of spectrum. We're using Compose and a software, in-house software, to handle this information, tunnel software, and use this traditional petroleomic tools to see our data. So here it's just to check if we're having asphaltenes with our extraction method to work on it. And you see, for example, just in this DPE carbon plot, you see specifically that asphaltenes behavior profile. It's completely different from maltenes and fluid, more aromatics, and more related to what have in literature. So we have, yes, you have a good way to fractionate the asphaltenes. And so because sometimes with, as I handle it here, I face with a complex mixture with a different compounds on it. Each compound has a different response on ionization. What you do to try to compare different fractions, we using the ionization efficiency, using here as I using the laser, proportional the number of laser shots to have and to attempt to have always the same intensity or the same number of ions if each scan. So we compared this ionization efficient, contrast this ionization efficient with the recovery. What you see, the occluded has a high ionization efficient compared, for example, with asphaltenes. So you have a very low amount of recovery here, but the response is so high. If I have a little bit of occluded or maltenes in asphaltene, what I see is just maltene or this type of compounds. I can't see the asphaltene on that. Then the extraction method need to be very precise. So the next step was characterize the fractions. We have different fractions in different polarities. Begin here with acetone and finish with TAF and methanol. We see here the comparison between the recovery and the ionization efficiency. The asphaltene and acetone fraction was more ionized easily, and the last one is more tricky to get a good standard of mass spec. And here on the right side, we have the normally plots that we normally use to characterize this type of fractions. And see, for example, the eptene toluene, more aromatic, more wide range of compounds detected. So here you don't have the IMPD on our instrument. What we did is select using CID, but unfortunately on the quad isolation, we send to the ICR. If I select a cardinal 550. I'm selecting a plenty number of ions. So why these selections to allow enough number of ions and see and just looking the behavior. And what you have here, it's different selection region of the mass spec. We have ions characteristics to the provenance from the island fragments and from archipelago fragments. So we're extending this characterization to the other fractions. You see, we see here different behaviors in these fractions, and so on. This behaviors is mainly due they broke the alkyl chains on archipelago type molecules, or just the alkylate the alkyl chains of the island type molecules. So you have two well-defined regions, but the yellow region I can have here island and archipelago structure. What you do next is try to automatize this interpretation, because it's normally done manually. You have a lot of peaks, and we create algorithm to do that using this behavior that we observed, you learning from these experiments. So you define the precursor ions, for example, the selection, the window of the white selection, and so define the lowest dBE for the precursor ion to monitor the archipelago type. So same dBE for the precursor, it's the fragments, and each fragment define the island, and you have here the yellow, the gap between the two regions. I can have the both structure. So based on that, we can have here a data that enable us to compare the different fractions. And you see, for example, the archipelago type are more concentrated, or it's more abundant on toluene D8F fractions. So the next step was perform the turbo scan analysis to see the stability. We performed this analysis during a long time, and what you see is more instables, and mainly the fractions that have more archipelago type structure found on this subfraction, specifically the toluene and toluene DAF fractions. So even you have this eptene toluene fraction, it's more this fraction are concentrated, this archipelago type. We develop a different way to reach these fractions, shorten this fraction time, because the previous method it's demand a long time, and to handle with a huge data set of samples, you need to have a high throughput way to perform these extractions. We just purify the asphaltenes and perform the solvent extraction with chocolates, and decreasing the weight using different series of solvent: acetone, acetonitrile, eptene, toluene. Mostly toluene fraction we finished with mostly more unstable compounds, and in a recovery related to 98.4%. What you see here, it's normally this fractional step method works similar. You have here, for example, the fragmentation show us, SMS show us that you have archipelago type and island structure on these spectra, and we performed the analysis using the turbo scan and confirmed that the toluene, eptene toluene, were the most unstable fractions on that. So now we are on investigation more deeply which compounds are there, and take different kind of asphaltene samples to see if it's correlated or not, and specifically perform some study on field. And regarding to the heteroatoms, we see that eptene toluene fractions has more sulfur compounds, more archipelago type structure, and ultimately one question was, if I have different type of crude oils, I can have different type of more concentrating archipelago or island structure. So we have here in the lab lacustrine marine oils. We perform these extractions. It is profile of these two samples, and we deeper characterize all these fractions, and performed some analysis using the archipelago fragments. What you see, it's not strictly related archipelago fragments to lacustrine or marine. We need more samples to test our hypothesis, but the asphaltene can be very useful to contain information to classify the oils according its origin, for example. So this is a summary of asphaltene characterization. You perform now some you have methods and using LEDI to characterize these samples and perform some stability measurements of that. And now jumping to the crude oil, what we normally do, the method is prepare the sample, dilute it in toluene, remove some 100 microliter diluted in methanol, and inject direct infusion on FT-ICR on SolariX system. And for APCI, PPI, you just diluted in toluene, diluted one more to reach 0.5 milligram per ml, and direct inject on FT-ICR MS. The workflow is normally they'll have a mass spec, and so put on composer and to assign molecular formula, and the sheets from composer we feed on tunnels to perform this type of plots and handle our information. Just to take a proof of concept here, we are our goal is use this information to classify oils or help in an organic geochemistry point of view. And we use this technique, the petroleomics, to study pre and post-salt Brazilian crude oils. These two crude oils are from different, were formed in different time and in different reservoirs. One is more not so deeper, other it's so deeper, and one is marine type. The post-salt is related to marine type 2, and pre-salt it's lacustrine type 1. So we have here this typical physical chemistry properties of these crude oils. We have 5 oils from pre-salt and 4 from post-salt. We're looking just the mass spec. You can't see any difference between these two oils. They look like similar. And diving on further on this technique, we see the power resolution using the 7 Tesla here, and the spacing of 14 normally seen on the crude oil analysis using Petroleomics. And here you represent the class profile from in electrospray negative mode from this type of oils. It's Brazilian crude oils are very known for the high content of nitrogen type compounds. You see always nitrogen, it's most abundant class, but here you have O and O2 classes. It's related to phenolic and carboxylic acids. And for now, the class behavior on the first level of information here just show us that we have some difference on this profile. So using the other strategies depending further on our data, analyzing the DBE distribution, for example, for O2 class, we see here from pre-salt clearly profile, mostly the aliphatic chain here, DBE1, it's more intensive. In other side, on their hands, the post-salt, it's not so preserved, it's more biodegraded. Then they have, for example, 2 or 3 rings more abundant here. So using the carbon numbers show strictly the same trend. So using the O2, you can easily, for example, for forensic purpose, classify these 2 different oils. And here we use acyclic. It's a DBE1 for cyclic compounds. The number of rings to 2, 3, 4, 2 or 6. And you have a ratio that can be very useful. You test this ratio for plenty of samples, it works, and a way to show that this data can be useful to classify oils according, for example, in sucrose for pre-salt and post-salt. And so plotting ternary plots here, the linear, the naphthenics, one rings, and the aromatic one, you can see a clearly trend here for these samples according to the total acid number. It's pretty impressive how it works. And move on. The other topic, it's related to the type, because the organic matter can be deposited over time in the lacustrine or the marine environments, and we apply that here in different Brazilian basins in a partnership with Petrobras. We study different basins in Brazil from different orange biodegradation and thermal evolution. The Brazilian reservoirs, mostly where normally we found crude oil petroleum here in Brazil, is related to the lift between the South America and Africa. So in the beginning, I have, for example, lagoons, and then it's start a seed, an open auction, and you have different type of environmentals here over the time. And it's reflected immediately in the environment of the petroleum was formed. So it's our proposal to use this methodology using both electric spray or APPI, the non-polar compounds, to classify this oil according to lacustrine or marine. But using the class E, it's easily classified using this methodology. But when I put here using APPI, for example, we have a plenty of samples. I have here lacustrine sweet, lacustrine saline, and marine in transitional with close related samples. You have, using the sulfur class S, we can organize in ternary plot just with class information. But unfortunately, the marine and lacustrine and transitional were not classified. So we tested this hypothesis using different basins. Unfortunately, you don't have plenty of numbers or equally numbers of samples for each classification, but our methods performed so well for a plenty of samples from different basins. So we clearly classified lacustrine sweet, lacustrine saline, and so on, deep in examination to scrutinize our DBE and carbon number distribution. We see some difference, some trends, and try to create new ratios, new parameters, new proxies to try to differentiate. And here you have an answer to classify these two types of samples, transitional and marine samples using this data. To organic geochemistry propose other point, it's some biodegradation. We need to perform this assessment of crude oil if biodegradate or not, because it's the value of the petroleum are decreased. So what during the biodegradation, the microorganism, the microbial is produce carboxylic acids, and you see here this profile increase the number of O2 class. You have here different type of samples, and mostly increase the DB distribution specifically for 2-3 ring, becoming this petroleum, this crude oil more acids. So we're using also to class, it's needed to classify these crude oils according to the level of biodegradation. We have here proposed AC index modified, contrasting with a typically biomarker used to classify these oils. Other attempt was understand the impact of thermal maturity on these polar compounds. The organic matter are deposited, and under pressure and temperature, it's transformed on crude oil, and the thermal maturity has a great impact on the crude oil, mainly on polar composition. Here we have different oils from different thermal maturities. What you see, it's more more degraded oil has a few peaks because the polar compounds was completely destroyed, releasing hydrocarbons. So you see here, strictly using the carbon numbers, we see clearly a shift to low carbon numbers because crack actions going on through this process, and the impact here from different type of oils related to the environmental deposition. Our goal was try to find a universal proxy to classify accordingly the oils according its thermal maturity. What you see is benzothiophenes. The benzothiophenes can be very useful. We plot the relative intensity using this ratio, and see, and you can classify the oils in 3 different types: a low, intermediate, or high thermal maturity. And we perform that, we apply that in different basins, and also we perform hydropyrolysis. It's a way to artificially simulate the thermal maturity process. And so you have these new markers here. Ultimately, work on thermal maturity. We see here the plots, the DBE plots, and the low to high. What we performed is a thermal maturity index. We call it EET from Portuguese name, but we divided in square areas this DBE carbon plots, and you have a number, and you apply that for different length of samples. You see according to the most thermal evolved samples, high thermal maturity samples has accordingly and the high IET here. So in summary, we present for you just some protocols, mainly on asphaltenes, but also when crude oil. We applied this information, this plenty of thousands of peaks to classify oils from different origin, migration, thermal maturity. And we are still looking for new markers. It's not easily tested, but nowadays using machine learning techniques or chemometric techniques, it's a hot point that we are still on investigation. And so trained for this type of oil. So Petroleomics has a very good job on classifying and studying this complex mixture. So once more again, I thank you, Brooker, for this kind invitation and the opportunity to show, and mostly my team, and also I thank you, Petrobras, that support my group. Thank you for everybody for the audience.
Thank you, Dr. Boniak. That was a very interesting webinar, and we had a lot of engaged attendees during your presentation. Very impressive, so thank you very much. We have time for just 1 or 2 questions. So I see one here in the question box. As you mentioned, HRMS FT-ICR is key instrument for oil samples. Have you considered ion mobility as another method of separation?
Yeah, ion mobility is has a great potential to apply to petroleum studies, because here we are facing with plenty of isomers. Each peak I detected, I have a molecular formula, but structurally it's related to a different isomers, and so on. It needs to be more deeply investigated, the potential of ion mobility to perform this kind of separation. Yeah, maybe in the future you have ion mobility together with the ICR commercially, and you can test that.
Excellent, thank you very much. That is it for our questions. If anyone else would like to throw in a question before the webinar is over, speak now. Raise your hand. If not, then we can conclude the webinar a little early. And thank you again, Dr. Boniak, for your time. Thank you very much for your presentation. And thank you everybody for attending our very interesting webinar today. And if you do think of any questions afterwards, you do have the opportunity to email us and we will forward it over to Dr. Boniak.
Okay.
All right. And with that, thank you very much. And I hope you all have a great rest of your day wherever you are in the world.
Bye, everyone.
Thank you, everybody. Hi, bye-bye.